Hello, this is the lecture 2.6, which is about limit at infinity and horizontal asymptotes. So the objectives of this lecture is to investigate the behavior of a given function when x becomes large. When we say becomes large, it means it goes to infinity or it goes to negative infinity. So we will evaluate this the limit of functions at infinity. For example, here is a function, which is a rational function, and we want to compare or evaluate the limit when x becomes large. It means x goes to infinity. We will also think about x approaches minus infinity, but let's start with x approaches infinity. So when we take some values for this function, starting from 0, here recall that my function is the following one, x squared, change the color, x squared minus 1 over x squared plus 1. Okay, so replace, substitute x by 0, you will find this value. X plus minus 1, you will find 0. And so on until you increase the absolute value of x. It means whether you approach infinity by setting x equal to 1,000, for example, or minus infinity. And in both cases, we will find that it is approaching 1. So we conjecture here that the limit equal to 1, and we will see by the rules that this also can be calculated to be equal to 1. So what happens for the graph? You see here then that the limit at infinity plus infinity and limit at minus infinity is equal to 1. We say that we have like this line here, which is horizontal asymptote. When we say horizontal, that means y equal to a number. And here the number is 1. Okay. So we conjecture this conclusion here that the limit at x infinity is equal to 1. Before, in the previous sections, we took limit of x approaches a number. Here we take x approaches infinity plus or minus. So that's the difference between this section and the previous ones. Here is the definition in general. If we have, we say that the limit of f of x, x approaches infinity is equal to L, when the value of the y, which is f of x, approaches the L as x becomes larger and larger. Okay, so intuitively we can think about taking x greater than certain number, x bigger than a, and in our mind that a is a large number. Let's think like, for example, 10 power 6. Okay, when we take x greater than this a number, then we will find that f of x must be very, very close to L. That's the meaning of the limit at infinity. So in terms of graph, you will have this situation, okay? So when we approach infinity, the function will approach the value L under or over the value L, or sometimes oscillating. We will see all these cases. Look at here, the function is over the horizontal line y equal to L. And in this third situation, it is oscillating, but it goes to L. You see that the amplitude of this oscillation is getting smaller and smaller when we go to x approaching infinity. So all the three situations may happen for the limit at when x approaches infinity and f of x approach L. So it can be L under the value y equal to L, or over the value, or oscillating around the value y equal to L. Here is our first example. Now, if we graph it using Desmos, for example, you see that we have this horizontal asymptote here, horizontal asymptote in the other side. And we conjecture that in fact, we find by calculator right now, and we will see later by the rules, that the limit at infinity is equal to 1, and the limit at minus infinity is equal to 1 as well. But this is not all the time the situation. Be carefully, we can have x approaches infinity. We may have horizontal asymptote, 1, and different one when x approaches minus infinity. Also, we may have horizontal asymptote here, but nothing here, okay, or the opposite. So all the situations are possible, but in general, we may have different situation for infinity and minus infinity, depending on the function, of course. So by the same way, intuitively, if we think that we are close to minus infinity for x, that means x less than a, and a is a negative number, very large in absolute value. Think, for example, about minus 10 power 6, same as we took for infinity, but with minus here. So the value of fx is approaching L. And the situation for the graphs looks like same thing, like what we did for plus infinity. So we may have this situation, or the oscillation as we did before. Now the definition 3 is what we call it horizontal asymptote. So once you find whether in plus infinity or minus infinity, the limit equal to certain number, L or L here, then we say that y equal to L, and here be carefully to write y equal to the number, not only the number. This is horizontal asymptote. Okay. As I said before, if the limits in plus or minus infinity they are different, so we will have two different horizontal asymptotes. Look at this example here. We want to find the limit of 1 of x, or when x approaches infinity. By a calculator, we see that if we take x very large, then clearly the value is approaching 0. So we conjecture that the limit of 1 over x when x approaches infinity is equal to 0. Same phenomena happens for minus infinity, because just you put minus here, so the result will be minus, and the value of the limit is 0, still 0 here. So we say that y equal to 0 is a horizontal asymptote for the function 1 over x. Okay. Here is the graph of the function, and clearly we have this horizontal asymptote here, y equal to 0. This is the horizontal asymptote. Now we have this theorem that we will use for in many situations. If you have r positive rational number, then 1 power x 1 over x power r is approaching 0 when x approach plus or minus infinity. Doesn't matter, since we will have x power r large for plus or minus infinity. So we'll use this theorem to evaluate now without calculator. We will use the rule to compute this limit here. Look at this. In general, when you have polynomial over polynomial, what do? You take, since x approaches infinity, you take the highest degree monomial in the first one, which is x squared in common factor. So x squared common factor of what? The first term here is 3, the remaining part of the common factor, minus. We have here x, but we took x squared in common factor. So I need to correct this by 1 over x. Then minus 2 to make it true. Then I will divide by x squared. And think how to obtain this term here. When you expand, okay, like that, you will find our expression here. So that's the deal that you make a common factor. It's like artificial, but when you expand, you should return to the original expression. I will do the same thing with taking the highest degree in the denominator, which is here x squared. So x squared factor 5 plus 4 over x plus 1 over x squared. And again here, if you want to verify your computation, just expand here, and you will find your expression here. Okay, now what happens? You see here, x squared, I will change color. This one and this one, they will cancel each other, okay, because they are common factor in the numerator and common factor in the denominator. Now I will use the previous theorem to conclude that this term and this term, and this one, all of them are going to 0 when x is large. Okay, so limit 0, 0. Okay, so what it remains here? It remains in the parentheses in the first one, 3. And in the second one here, 5. So basically, I will have the limit equal to 3 over 5. So that's my conclusion. The limit is equal to 3 over 5. And here, no difference to compute x approach infinity or x approach minus infinity. So the result will be the same. And my conclusion is that y equal to 3 over 5 is horizontal asymptote. Okay. So this is what it is done in the next slides. And here is the graph, how it comes to be seen in the graph. And you see here the situation. In infinity, we are below the horizontal asymptote. In minus infinity, we are above the horizontal asymptote. Look at this example 3 now. And here we have to pay attention to the square root. We will make basically the same process, but we will be carefully of the square root when we took out the common factor. So my expression, if by the way, if I substitute the value of x infinity, basically I will find in the numerator infinity and in the denominator infinity. This is indeterminate form, by the way. And let me recall all the indeterminate forms that we have in general. The first one that we see is 0 over 0. Okay. Second one, 0 times infinity. Third one, this one. And there is another one, which is number 4, which is plus infinity minus infinity. Okay, so when you add two different sign limits, one is plus, the other is minus infinity. Whatever you do, this is indeterminate form. It's not, if you have plus infinity, that's okay. This is plus infinity. If you have minus infinity, that's okay also. It's minus infinity. But if you have different, you add two different, plus one is plus, the other is minus. This is indeterminate form. That means we have to continue and change the expression to remove this indetermination. Okay, so we have to continue here. We are in the situation 3 here, since we have infinity over infinity for x approaches to infinity. So we need to change the expression of the function, and here we will factor in the numerator by x squared. So again, x squared factor 2 plus 1 over x squared. To make place, let me remove some data here. Okay. And over, in the numerator, the highest degree is x. So I will take x in common factor. 3 minus 5 over x. Now I will use the theorem of limit 1 over x power r to conclude. You remember here, this term will go to 0. This term will go to 0. But still, I didn't here do the simplification because I didn't take out the x squared. And here is the danger. We need to be carefully for this common factor when we take out of the root, because here we will have root x squared times root 2 plus 1 over x squared. And the problem may come from here, because root x squared is exactly absolute value of x. And absolute value of x, it has two expressions depending on the sign of x. It is x if x is positive, and minus x if x is negative. Okay? This x is negative. So since we are here approaching infinity, so the absolute value of x is x. In this situation, if we work with minus infinity, then I will take minus x, but here I will take x. And you see here, so I will replace all this expression by x. And here comes the simplification. Look at the function f of x now. It will give x root 2 plus 1 over x squared over x 3 minus 5 over x. Okay, now working with the limit, this will go to 0. This one will go to 0. And this cancel. So the result is equal to root 2 over 3. Okay, so we conclude here that directly, we don't need to conclude the asymptote. Once you have the limit in infinity or minus infinity, one of them is equal to a number, then this is horizontal asymptote in any case. So here y equal to root 2 over 3 is a horizontal asymptote. What happens for x approaches minus infinity? Basically, we will use the same thing. The only difference is that absolute value of x will be equal to minus x in this case. And you guess that the result will be minus root 2 over 3. So the horizontal asymptotes are plus minus root 2 over 3. And we are done with this example. Okay, so these are the horizontal asymptote. If we think about the vertical asymptote for the function that we took here, this function, this one here. Okay, so for vertical asymptote, and let me recall you something here. If we want to find the vertical asymptote, what is the vertical asymptote? It is limit at x approaches a number a, and the result, the L, is plus or minus infinity. That's the vertical asymptote. It is the opposite, exactly the opposite to the horizontal asymptote. The horizontal asymptote, you take x approaches plus or minus infinity, and the limit will be a number, a. Okay, so it's totally the opposite. That's the limit. Okay. Okay. And now it's clear for the horizontal asymptote. You just take plus infinity and you take minus infinity and verify all the time that do these two limits, because sometimes they are different, and you conclude the horizontal asymptote. However, for the vertical asymptote, how to proceed to that? In general, take the denominator equal to 0, okay? And this is not necessarily all the time the vertical, it will give a vertical asymptote, but it's like a candidate for the vertical asymptote, and you need to confirm that this candidate is a vertical asymptote by finding that the limit is plus or minus infinity. So here the candidates for the vertical asymptote are coming from 3x minus 5 equal to 0. That means x equal to 5 over 3. So this is possible vertical asymptote. How to conclude that? We compute the limit at this point, 5 over 3. Since we cannot put 5 over 3, I will put 5 over 3 plus and 5 over 3 minus if we need that. But you can conclude once you do for one of them. It's not like the horizontal asymptote. Here, for the vertical, if you find for A plus, then it is vertical asymptote. If you find for A minus, it is vertical asymptote. If you find for A itself, yes, it is vertical asymptote. It is one of them is sufficient to conclude the vertical asymptote. So here, when x approaches 5, 3 plus, clearly this one will go to 0 plus, and the numerator, when you replace, it's a number. Star, let's call it, it is a positive number. So positive number over 0 plus, this positive number is not equal to 0, of course. This positive number over 0 plus, it will give plus infinity, and this is sufficient to say that x equal to 5 over 3 is a vertical asymptote. You don't need to do for 5 over 3 minus. Although here is the conclusion, but it is not necessary. Look at this try and check now. Find the horizontal and vertical asymptote of the graph of the function. So I will start here by question number 1 for the horizontal asymptote. Let me call it HA, the horizontal asymptote. So I need to compute limit x approaches plus infinity for this expression. And clearly when we substitute, this is infinity over infinity, so it won't give a conclusion. So I will take common factor x squared in the numerator. So 1 plus 4 over x plus 4 over x squared. All the time, if you don't understand how we obtain this, just expand and you will find the result in the original function. Over the highest degree in the denominator is x cubed. So I will take x cubed common factor, 1 minus 1 over x minus 6 over x squared. And now clearly these quantities, all of them are going to 0. Okay. So, and here simplification of x squared with x cubed. So it will be power 1 here. And the result will be like limit 1 over x when x approaches infinity. This is equal to 0. Okay, so clearly y equal to 0 is a horizontal asymptote. We don't need to do minus infinity here, since the computations are the same. We didn't do any difference for x plus or minus infinity. It's the same. There is no root, there is no absolute value to make the difference. So y equal to 0 is horizontal asymptote. Now, what about vertical asymptote? So for vertical asymptote, let's call it VA. The candidates are coming from the resolution of x cubed minus x squared minus 6x equal to 0. We take x common factor, and this is x squared minus x minus 6. We continue factoring. So x minus 3 times x plus 2 equal to 0. And we have 3 candidates. So whether x equal to 0 or x equal to 3 or x equal to minus 2. So I need to study all of them to see if they are vertical asymptote or not. Okay, how to do that? We need to compute the limit when x approaches 0 or 3 or minus 2. And if necessarily, we will do 0 plus 0 minus, 3 plus 3 minus if necessary. Okay, so here, what I will use, the factoring of both functions. So I will remove this and write my function as, so still 1, f of x with factoring. So it's x factor x minus 3, x plus 2. This is for the denominator. What about the numerator? It's x plus 2 squared, that I write x plus 2, x plus 2. Okay, so there is clearly simplification by x plus 2 in the limit. So when I compute limit f of x, let me start with the x approaches minus 2, because this is the easiest one. So it will be equal to 0 over minus 2 times minus 2 minus 3. Anyway, it is 0 over non-zero number. So it is 10, I guess. So it's equal to 0. That means that x equal to minus 2 is not a vertical asymptote, since the limit is not plus or minus infinity. So this is excluded. And you see here that it was a possible candidate, but we concluded that it is not vertical asymptote. X equal to minus 2 is not a vertical asymptote. Okay. Now, what about x approaches 3? For x equal to minus 3, is it a vertical asymptote? Then we need to compute since I cannot replace x by 3, so I will compute x approaches 3 plus of, if you remember, it was x plus 2 over x times x minus 3. So if x approaches 3 plus, this term here will go to 0 plus. This is like 3, and this is like 5. So it's somehow like 3 times 0 plus. This will give 0 plus. So it's like 5 over 0 plus. This will give limit equal to infinity, and we conclude here, it is enough to conclude that x equal to 3 is a vertical asymptote. Okay. So, and in the same way, we will do for x equal to 0, because you see here when x equal to 0, this approaches 0 plus, then this is minus 3, this is 2, 2 over 0 minus, it will give minus infinity, so I will do it anyway. So for x equal to 0, I have my limit x approaches 0 plus. As I said, I cannot put 0 here because I will have a division by 0. So it's 0 plus x plus 2 over x times x minus 3. Okay, what happens for this? When x approaches 0 plus, this will approach minus 3. But this will approach 0 plus. 0 plus times minus 3, this will give 0 minus, because minus 3 is negative times 0 plus, which is positive, it will be a negative number. This one here, it will go to 2. Okay, so 2 over 0 minus, that will give minus infinity, and x equal to 0 is a vertical asymptote. Okay, that's for part 1. Now we will go for second equation. Limit of arctan when x approaches 2 plus. Look at here, x approaches, so we are in this example here, x approaches 2 plus. That means that x minus 2 approaches 0, 0 plus. What about 1 over x minus 2? It will approach, it's like 1 over 0 plus, so plus infinity. What about arctan of plus infinity? This will be somehow equal to pi over 2. This is the limit of arctan. So the limit is equal to pi over 2 because if you remember the graph of arctan is something like that. This is pi over 2 minus pi over 2. And the graph is doing something like so. Okay, so the limit at plus infinity is pi over 2, at minus infinity is minus pi over 2. And since we have arctan of something going to plus infinity, so the limit is pi over 2. What about the limit of sine x when x approaches infinity? Look at this. The graph of sine is something like that. It continues forever like that. Okay, so if we think about x going to infinity, clearly there is no value where the function is approaching. So still it oscillates from 1 to minus 1. Okay, so we cannot have this limit. And another way to think about this limit, so the limit does not exist here, if we can conclude, does not exist. Same thing for cosine also. And even for tan, we don't have limit at infinity. How to understand this second limit? Think about x very large. So I will take x equal to, for example, 2n pi. And n, I will take it 10 power 6, let's say. This is large, very, very large number. Very big, this number. Okay, so it's like x approaches infinity, this one. What happens for the sine? Sine 2n pi, since it is multiple of 2 pi, so this is equal to 0. And if I choose another x, which is also large, let's say x equal to pi over 2 plus 2n pi, I know that, let's call this x1, and this is x2. So sine of x2 is equal exactly, since sine is 2 pi periodic, it's periodic, so it's sine pi over 2, which is equal to 1. So I took two values x1 and x2, both of them going to infinity, but I find one is approaching 0, the other one is approaching 1. So it's not one single value that makes the limit. So that's why the limit does not exist here. Okay, by this example, we can go to the limit now, the infinite limit at infinity. So we see, if you remember, limit at a number giving a number, L, limit at a number giving infinity, and the third case is limit at infinity giving also infinity. Okay. So if we take this example, x cubed, for example, and try to take x very large, then the limit will clearly be equal to infinity. However, for x approaching minus infinity limit of x cubed, here, of course, if we substitute some large value with negative values, so we will find that it is going to minus infinity. So depending on plus or minus infinity, we will find the limit of the function. So here for the x cubed, we know the graph of the function x cubed, and we clearly have the limit when x approaches the infinity is going to infinity, and when x approaches minus infinity, it is going to minus infinity. It's not the case for x squared, for example. When you say x squared is something like that. So both in plus infinity or in minus infinity, the limit is going to infinity. Let us finish by the try and check example here. The substitution here, of course, will give indeterminate case, since this term will go to plus infinity and this one will go to minus infinity. This is indeterminate form. So we need to factor. The best way is to take common factor, which is x squared, factor 1 minus 1 over x. Okay. And here, clearly, this will go to 0. And all this will go to 1 then. And you have the limit of x squared is equal to plus infinity. So plus infinity times 1 is plus infinity. Okay. The second example, same thing. We will, if we substitute, then it is indeterminate form, infinity over minus infinity. So better to make the factoring here. So x squared factor 1 plus 1 over x factor 3 over x minus 1. Okay, so x squared with the x will cancel, and the limit here goes to 1. This limit is going to minus infinity. It is important to compute these limits, because you see here the sign will give the conclusion for the limit. So although the limit is infinite, but it can be plus or minus infinity. Okay, so here this x will go to infinity, and with this minus 1 over minus 1, this is minus 1. Minus 1 times infinity, that's minus infinity. The last example, here again, it is indeterminate form, since this will go to minus infinity, but this term will go to plus infinity. So this is indeterminate form. What we do, if we have a root, in general, we will think about the conjugate. So I will remove this indetermination by computing the conjugate, multiplying by the conjugate. What is the conjugate here? It is the same expression, but with minus between the two terms. So I will put this in parentheses, and then I will multiply by the conjugate, which is x minus root x squared plus 1. Since I multiplied by this, then I need to divide by the same thing. x minus root x squared plus 1. And don't be afraid about this minus here. Everything will be arranged when we compute the limit, you will see. Here is the form of a plus b times a minus b. That's the purpose of the conjugate, and clearly you put it directly, it's equal to a squared minus b squared, since we know this formula. So my conclusion will be limit x approaches minus infinity of x squared minus, and here be carefully, what it is inside the square root is x squared plus 1, but there is minus in front of them, so I will put parentheses, x squared plus 1. And if you remove the parentheses, you will see that it is minus x squared minus 1 and over x minus root x squared plus 1. Okay, now removing the parentheses, I will replace this directly by minus here. So it is minus. Then this will cancel this, and I have minus 1 in the numerator. What about the denominator? Here, it will go to minus infinity. And this one also will go to minus infinity. So the denominator will go, all the denominator will go to minus infinity. And that's the difference here, minus infinity, minus infinity. This will give minus infinity. It's not indeterminate form. So I have minus 1 over minus infinity. That will give 0 as result. Okay, so this limit is equal to 0. And by that, we are done with the lecture 2.6. Thank you so much.